Welcome to this lesson. This lesson is about embeddings, which is very important concept in machine learning. So embeddings are vectors, each a list of numbers that represent. This numerical transformation is a bridge between the human world of language and the machine world of numbers. In machine learning, dealing with raw text data can be challenging. Machines prefer numbers, which is where embeddings come in, converting text into a format that machine can easily understand and process. These numerical representations also preserve the semantic information of words. Words that are semantically similar will have embeddings that are numerically close. Embeddings are rich in information. They exist in very high dimensional space, with each dimension capturing different aspects of the input text, thus preserving the complexity and nuance of language. For instance, the word example might be represented by a 5-dimensional vector that we see here. These are 5 numbers in a 5-dimensional vector that are representing the word example, which is just an example. Real embeddings often have many more dimensions, thousands, but this example gives you an idea of what they might look like. Okay, let us go to the code now and see how we obtain embeddings using the OpenAI APIs. So if we go to Visual Studio Code, in the controllers, I will create a new controller. I will call it Embedding Controller. .js, of course. Okay, on this embedding controller, I will import the API configuration. Okay, so then I will create the function getEmbedding. Here I export this function using the imports module. Of course, the cosine similarity we haven't implemented yet, so I am taking it out. Okay, then we will make a call to the create embedding endpoint in the OpenAI. Of course, as you can see, the OpenAI.create embedding is an asynchronous method, so I am using the await, and that's why I have specified the async here. Then we come to the response. We save the response, which contains the actual embedding. Of course, this will take some time, but we will keep waiting because of the await keyword. Okay, then I add the model parameter. The most famous embedding model in the OpenAI APIs is text-embedding-ada-002. So this is the one that we will be using throughout the course. Okay, then I will add the text to be encoded or to get the embeddings, the corresponding vector for this text. Of course, this text is passed to the function. Okay, the next step, I will parse the returned response in order to get the actual embedding vector. So here you can see I added the console log. It is commented out because in this case I want to return the value, but as you can see, the value contains the response, contains data inside it, an array of data inside it, and embedding. This return value represents the vector that we are returning. Let's go to the playground and call this API. Okay, so I'll go to playground, and at the top here I will add import for this new controller. So that's this new controller. Cosine similarity we still didn't define, so I'll change it here. Then at the end we add a new comment section for embedding. Okay, now let's make the call to this function that we imported. RL read line question. We are asking the user to enter text to embed. Then we will pass a function that will be called then. Here is this function. This is an anonymous function that provides a text parameter and calls the generate embedding. Of course, generate embedding takes time. It is asynchronous. So I attach a then block. Now in this then block, I am going to print the actual embedding that we are getting. So here I will be consoling out the embedding that we have received. So go Node Playground. It's asking me to enter a text. This is a nice day. Click enter. Okay, you can see that we got the embedding. The embedding is just a list or a vector of floating point numbers. You can see it displayed 100, but there are 1436 remaining. Because for this model that we have called text embedding ADA02, it returns embeddings with 1536 dimension. Now each of these dimensions capture a certain aspect of the sentence. If it is a statement or a question, if it is in the past or in the present. Each of these dimensions, the 1536, capture a certain aspect of this sentence. Okay, let's get back to the slides and understand what is similarity in embeddings. It is a very important concept. In the world of embeddings, similarity is based on context, not spelling. Words used in similar context will have a numerically similar embeddings. The distance between embeddings represent their semantic relatedness. So if two words are used in similar context, their embeddings will be close together in the high dimensional space. Context is crucial in real M of embeddings. The numerical closeness of embedding is determined by how often words appear in similar context. For example, the words goat and cow might be considered similar because they are often used in the same context in language, resulting in a numerically close embeddings. On the other hand, capital and capital, despite being close in spelling, may not share similar context and hence may not have close embeddings. So embeddings determine or is determined by the semantic meaning of the words and phrases, not on the spelling. They have no idea of spelling, they have an idea of context. So this is similarity. Now, how do we measure similarity? We measure similarity by calculating what we call cosine distance. Cosine similarity is a measure that gives us an understanding of how similar two vectors are. This measure takes into account the orientation of the vectors rather than just the distance between them. Essentially, it helps us understand how closely aligned the vectors are in terms of their direction. In the context of cosine similarity, the angle between the vectors matter. The closer the vectors, the smaller the angle between them, and thus the cosine of the angle is closer to 1. So we'll be calculating cosine similarity. If the similarity is close to 1, we will say that these are high similar vectors. If it is closer to 0, then they will be less similar. Of course, this implies that if two vectors are pointing in roughly the same direction, they are considered highly similar. Now, cosine similarity plays a critical role in natural language processing tasks. It provides us with a precise tool to measure the semantic similarity between different words or phrases. By comparing the cosine similarity of the embeddings of two words, we can quantify how similar their meanings are. Let's consider a practical example to illustrate this. If we have embeddings for the words milk and cappuccino, the cosine similarity between these embeddings will tell us how semantically similar these words are. If the vectors point in similar direction, the angle between them is small, and so the cosine similarity is closer to 1. It suggests that these words are likely to have related meanings. Okay, let's go back to the code and calculate cosine similarity. So I'll go back to the embedding controller. Here we will add 3 utility functions. So these are the three functions that we will look at. The first function is cosine similarity. You pass two vectors and you calculate the cosine of the angle between them. If this value is closer to 1, then the two vectors are semantically close. If it is closer to 0, then they are not close. Of course, the cosine similarity, this is not a math class. You don't need to understand this, but just very quickly, it represents the dot product of the two vectors multiplied by the mean square values of both vectors multiplied to each other. Now, the dot product is just multiplying each element in each vector and adding this to a complete sum. The normalization is getting the square of each dimension in the vector, then sum that, then get the square root of this sum. The cosine similarity is just the dot product of these over the normal sum for vector A times vector B. As I said, you don't really need to understand this, but you need to know that if you have vector A and vector B, you can calculate the cosine similarity of these two vectors. If the cosine similarity is close to 1, then these two vectors are similar. If the cosine similarity is closer to 0, then they are far away and not similar. So let me expose this function, cosine similarity. Let's go back to the playground. Okay, let me now just get these two examples, and this is the call for the generate embedding. In fact, at the top, we need to also import the cosine similarity. So we add it here. Now we have at the top the cosine similarity. Let's go back to this generate embedding method that we are calling. Okay, so I added the then statement. Of course, this is the generate embedding. It takes text1, which we have defined here. It returns a promise because it is asynchronous, and it will call us with the parameter of the embedding. Because if we come back here, you see that this function generate embedding returns the embedding. So this is the embedding that is passed to us in the then block. Okay, then we make a call for another version of generate embedding, but now with text2. So the first generate embedding was called for text1. We waited until that returned. We got the embedding for text1. Then we generate another call using text2. We attach a then block, and later we will get embedding 2. So now we console log the cosine similarity between embedding 1, which is for text1, and embedding 2, which is for text2. So all what we did here is that we made a call to generate embedding. We passed text1, which we defined here. Then we attach then a block. We will be called with the embedding when it is ready. We will make another embedding call for text2. Then we attach then a block, and then we will be called when embedding 2 is available. Now, once these two are available, we will call the cosine similarity that we defined here, this cosine similarity. Okay, so let's go and test these things. So I have text1 set to capital and text2 set to capital. Now, they are spelling similarly, but in context they are not related. Our expectation is that these two embeddings will not be similar, they will not be close. So let's see what it is. Let me start playground. Okay, I still have a code that I should comment out at the beginning here, so let me comment this code out. Okay. Let me clear the screen. Now let's start this. Okay, we got that the similarity is 0.86. Of course, they have a lot in common. They are both nouns. They have some relation, but we saw that it is 0.868. It's not close to 1. Let me stop this and call for go cow and goat, and let me comment these out. Okay, let me run that again. Okay, as you can see, they are closer to each other. Here we have 0.88, while here we have 0.868. So that's because cow and goat are used in the same context usually, and the cosine similarity of the two embedding vectors are a measure of similarity. Capital and capital, they were less similar. So they are actually still similar to a certain degree, but they are not as similar as cow and goat. Okay, so now let us bring other strings to test with. So I will come here, I will comment this out. Now here I have text 1 and text 2. Notice text 1 is saying the boy playing in the street. The second one is saying the kid having fun in the road. So it's a kid, not boy. It's having fun, not playing. It is road, not street. Yet semantically, these two words almost mean the same things, or two sentences, because the boy playing in the street means the kid having fun in the road. Now they are written spelling, they are completely different words. But let's see how close they are to each other. So let me try here. Yes, they are very close, although there are two statements with almost no similar words, but they, by all results, they are very close to each other because they are having the same semantic meaning. Okay, let me change the input. So let me text 2. It is a wonderful morning. So this is text 1, this is text 2. Now let's try and run this again. Okay, so they are not very similar. They are just 0.76, the cosine similarity between these two vectors. Okay, let's bring some more examples. Okay, so let me comment this and comment this. Okay, so the doctor made an operation. Text 2, the doctor made 2 operations. How similar? I think these are very similar, but let's test that. As you can see, they are very similar, 0.95, because both are talking about a doctor who is doing operations. One is one operation, the other is 2, but still they are very similar. Okay, let's do the sergeant made a surgery. The sergeant made a surgery. Now again, they are very similar in meaning, but they are written completely differently. Let me do this. You can see the cosine similarity is very high, although they are written in different manner. Okay, let's comment out text 2. Okay, now let's have text 2, the engineer fixed the motor. I will save. Let's try now. Okay, 0.81. So they are both statements and so on. So they have some similarity, but it's just 0.81. While for the previous two, it was 0.93 and 0.94. Okay, let's see the last example. Text 1, I'll keep it the same. I'll change text 2 a little bit. Now, did the engineer fix the motor? Now, this version of text 2, it is the different context, similar to the one we looked at here, but it is a question. So I expect that this will be further below the previous one because they are not the same now. They are not statements. One of them is a question and one of them is a statement. So let me try now. Save first. Okay, it is 0.79. Of course, the previous one, it was 0.81 because they are not close. But they were both statements and so on. When I convert it to question, it is even less close because some dimensions of the embedding are not satisfied anymore. Thank you.